In section 3, I give a brief introduction to the analysis of binary outcomes. If you look at a model graph, top left here, we have a latent variable f influencing 5 observed variables. In this case, the 5 observed variables are binary. And the question is, what should we mean by these arrows from f to the y's? Well, we encountered that in 3 different contexts: item response theory, factor analysis, and also now with the random intercept, where this is a random intercept latent variable. The meaning of this is really what we have on the right, where on the x-axis we have the factor f with the distribution, and the y-axis then shows the probability of getting a response of y equals 1 for different values of f. So take for instance a situation of testing of math ability, which is a common situation in item response theory. Then you have 5 different curves, one for each of the 5 items. And for, say, an average value of the ability, you have for this item a fairly low probability of getting it correct. Whereas for the higher ability, you have a high probability of getting it correct. So that's a fairly difficult item. If you look at the average ability level here, we said it was a low probability of getting that item right, but this item or these 2 items have a higher probability of getting correctly. That is, they are easier items. So shifting curves sideways has to do with the easiness or difficulty of the item, and that's why we use the term item difficulty there. Whereas the slope, the steepness of these curves have to do with so-called discrimination. In factor analysis, we instead talk about item thresholds and factor loadings. Item thresholds is then a counterpart to the item difficulty. It's a term that we use because it's convenient to talk in terms of thresholds when you move from binary to polynomous outcomes, as we will see in a few slides. Now, the typical specification here then is a normally distributed latent variable. That's what's used in item response theory. And then you have a choice between logistic or probit regressions. So these curves are either probit curves or loaded curves, often hard to distinguish in terms of practical applications. In IRT, it's very common to use logistic regression, but probit regression could be used equally well. If all of this seems a little bit unfamiliar to you, you may want to take a refresher study of short course topic 2, which is we have video and handouts for on our Mplus website. We offer in Mplus estimation by WSMV, the weighted least squares estimator, maximum likelihood, and Bayes for these situations, so applicable to item response theory, factor analysis, and random intercept modeling. And we have a nice little fact on the choices between these 3 estimators for categorical outcomes in general, pluses and minuses depending on various aspects of your application, number of factors, number of items, and number of people. So that's a fact that I recommend reading. Now turning to slide 26 then. We want to introduce an equivalent representation of this model, of these curves, probability curves, using a continuous latent response variable y star behind each of the observed binary variables. So we draw them as continuous latent variables here, with the idea that you answer the item in a certain way depending on whether the y star variable is above a threshold or not. So for instance, in the math ability situation, you have a math ability, but then y star 1 is the specific ability that is relevant to solving item y1. So that specific ability, when it exceeds a threshold, you get the item right. But when it doesn't, when it falls below the threshold, you get the item wrong. So that acknowledges that the specific Y star ability can be very close to the threshold, just above the threshold, getting the item right, or far above the threshold, where you are surely going to get the item right. So it shows that, or indicates that you believe that you could have measured it in more continuous fashion, but you're settling for a binary measurement. Now, specifying a normally distributed factor together with probit regressions, that is the regressions between the factor and the observed variables, those S-shaped curves on the previous slide, that is the same as specifying normally distributed latent response variable Y star. So if F is normal and these relationships between Y and F are probit, then the Y stars will be normal. So it's like saying that normal F plus normal residuals here, normal plus normal, becomes normal. If you have logistic regressions, then you do not get Y star normality. And we're going to work with this probit context. So we're going to talk about multivariate probit models. So they are models for normally distributed Y star variables. Of course, the normal distribution may not always be correct, but we're going to take a close look at the fit to the data to see when that's a good approximation or not. Now, the correlations then are going to be focusing on the Y stars, not between the Ys. So latent correlations, or correlations between latent variables. And in the case of categorical or binary outcomes, those correlations are called tetrachorics. With polynomous outcomes, they become polychorics. On slide 27, we take this a little bit further. So in the cross-sectional modeling that we're looking at for IRT and factor analysis, you focus on the relationship between F and Y. But the longitudinal modeling of panel data analysis adds a focus to that, namely the relationship between the Ys at different time points, the dynamic aspect, with the idea that the factor alone cannot account for all the correlations among the Y stars. So you have a factor here, but in addition to it making Y1 and Y2 correlated, for instance, you also have a regression of Y2 on Y1, Y3 on Y2, etc. So even conditional on the factor I here, the random intercept in this case, Y1 and Y2 are not independent, but they are correlated because the Y stars are correlated. So you have an auto-regressive correlation here. Now, once you've formulated the model in terms of continuous latent response variables Y star, you're getting into multivariate probit modeling, which allows linear regressions among these Y stars. So linear regression in the customary fashion, albeit among continuous latent variables. And what we've drawn here is actually the DRI-AR1 model. That is, you have a random intercept, but the dynamic phenomenon is between the variables, not between the observed variables, mind you, but between the continuous latent response variables. But the important distinction is that the random intercept influences the variables for which there is a dynamic relationship. So this is not an RI-AR1 model, but a DRI-AR1 model. Now you can generalize this idea of latent response variables to polynomous outcomes, so ordinal ordered categorical outcomes. So here you have a picture of two variables, J and K, and the marginal distribution is like this. You have a high percentage at the highest point here, highest category, 5 categories. So you have a ceiling effect. And with 5 categories, that means you can think of that as 4 thresholds on a continuous latent response variable Y star sub J. Likewise, for the other variable, you have a strong ceiling effect with 5 categories, so you have 4 thresholds here. And the underlying bivariate distribution looks like this. So it's the fact that you have ceiling effects here, it's just that your response categories do not cover the latent response variable distribution very well, but are shifted to one end, the low end of that. But the advantage here when you have ordinal variables is that you still have one single regression between y star j and y star k. Ordinal variables result in one regression as opposed to the nominal case. So doing this transformation or translation into underlying normal y stars makes it possible to do quite general latent response variable modeling, including RI-CLPM. And this is available in Mplus both for the weighted least squares estimator and the Bayes estimator. On slide 29, I want to point out that there really are two kinds of model assessments for categorical outcomes that you need to pay attention to. We're used to fitting a model to a set of correlations, sample correlations. In this case, tetrachoric correlations among a set of normal continuous latent response variable. And that can be done in both WSMV and Bayes, as I mentioned. That kind of fit was described in Mutén and others in my 1997 paper, which I left unpublished, but is quite influential, I must say. Robust inference using weighted least squares. And you see the URL here. You can click on it and get to that article. So that gives the underpinnings of WSMV. Now, there's the other way of looking at fit, namely the fit to the data in the form of response patterns. That is a frequency table for all variables. So if you have all 5 variables, you have a 5 by 5, etc. a 2 by 2 by 2 by 2 frequency table. And the interesting thing here is that a model may fit the y-star correlations quite well, but not the frequency table. So even a just identified y-star model with all widths, that is all covariances or correlations between the variables, an unrestricted model, may not fit the frequency table in some cases. And I pointed that out already in 1993 in a chapter in a book by Boland and Long, and you have the URL connection here at the bottom of the page. And that's something we have to pay attention to here when it comes to cross-lagged panel modeling. On the next slide, I talked a little bit more in detail about this. First, the fit of y-star correlations. So that states that the WSMV chi-square works well when the number of variables is not large and the sample size is not small. So that is a perfect case then for cross-lagged panel modeling. Chi-square doesn't work as well when the number of variables increases and the sample size is small. Now for Bayes, you have the so-called PPP idea, where you build on the idea of posterior predictive checking to get a posterior predictive p-value. So using any fit statistic, not only chi-square, but like how well does the distal outcome fit, you can compute the fit statistic for the observed data and then generate the fit statistic distribution based on generated data from the estimated model and find the proportion of cases where the latter is larger than the former. So you just compare these two quantities and get a p-value for the model. And the higher the p, the better the model. Bayes PPP for categorical variables is based on chi-square test of overall model fit for the y-stars. And it's analogous to the WSMV chi-square test of estimated versus sample tetrachorics and polychorics. But it does have the disadvantage of low power for binary outcomes and being less powerful than the WSMV chi-square test, as we point out in this article here that we have updated to a 2021 version. You have the references on the last couple of slides. But the Bayes PPP is more powerful for polytomous variables, so that gives us some hope there. Now continuing and looking at the other kind of fit, the fit to the data in terms of frequency table, we of course have a standard frequency table model fit in categorical data analysis using both Pearson and likelihood ratio chi-square tests, where you sum over all of the cells of the table. So with 5 variables you have 2 by 2, etc., 32 cells. And it's observed minus the model estimated quantity squared divided by the estimated. And likelihood ratio looks a little bit different, but asymptotically they have the same statistical properties of being chi-square distributed. But typically in our applications there are too many frequency table cells, with many cells having 0 frequencies. And then the tests don't work well and they disagree. For instance, with 8 binary variables, we're going to talk about that quite a lot in our analysis over 8 time points. You have 2 to the power of 8, namely 256 possible response patterns, where many patterns are probably not observed, 0 cells in the frequency table. And the 2 tests will disagree strongly. And of course, if you have a bivariate cross-lagged model over 8 time points, you have 16 variables, and 2 to the power of 16 will be a very large number. What you can do in that situation is to collapse from the multivariate frequency table down to univariate and bivariate frequency tables, where you have higher frequencies and where statistics will work better. That comes out in new Tech 10 for both WSMV and Bayes in version 8.7 and also in version 8.8. Where you get standardized residuals for response patterns. We're going to focus on the 20 most frequent patterns, and uni and bivariate frequency tables, plus Bayes PPP for Pearson, fit to uni and bivariate tables. So let's take an example here. A frequency table fit for dataset 2, this suicidal ideation and substance abuse example. Sample size 737. And we have 8 time points. So we're going to consider a so-called all-with model, which is then an unrestricted, freely correlated model. So we say Y1 through Z8, Y being suicidal ideation, and Z being substance abuse, from the first to the last time point, freely correlate with each other. So for these 16 variables, the most frequent pattern is zeros for both variables at all time points. Nobody shows any of these phenomena, and that's observed for 104 individuals, which is 14% of the total sample. And that's an important thing to note, how many are in this most frequent pattern, because with categorical data, a general problem is that in many applications there's not enough change over time. And if variables don't change over time, you can't really talk about cross-lagged effects. We're going to consider both WSMV and Bayes in this application. And if you're new to Bayes, you may want to take a quick introduction to Bayes estimation in Mplus by taking a look at Mplus short course topic 12, parts 3 to 4, slides 4 to 21. So very short part here, which gives you the essence of Bayes estimation. So on the left you have the input for WSMV, and on the right you have the input for Bayes. So WSMV is the estimator, and we will choose parameterization equals theta, because we're going to be able to talk about residual variance specifications a little bit later on. And the model is simply what I just mentioned, Y1 through Y8 covariate with Z1 through Z8. In Bayes, it's equally easy. Estimator equals Bayes. We want to keep an eye more keenly on the iterations to see that they're converged, and that's described in this short course topic. And here's a good default setting for that. And the model is the same, Y1 through Y8 with Z1 through Z8. And with Bayes, we always want to take a look at Tech 8 to make sure that the process has iterated its way to a converged solution in a good way. So then on slide 33, we look at what kind of fit information we get here. WSMV on the left and base on the right. So we have 136 parameters here in terms of the proportions and correlations for these variables, for these 8 variables. 8 plus 8, 16 variables, I should say. Chi-square test of model fit is 0 with 0 degrees freedom because this is an unrestricted, perfectly fitting model. So the p-value would be 0 with WSMV, as we would expect. But that doesn't mean that it fits the data perfectly. So we take a look at that second aspect of fit here. But by first looking at most frequent response patterns, and we list the 20 most frequent to make life a little easier. So we have different response patterns in terms of the zeros and ones over the time points. And which ones they are listed above here. And you have observed frequency in this column and model estimated frequency here. And you see that observed is 104 and estimated 98, not too far away from each other. And then you have a standardized residual. And since it's not greater than 1.96, it is not significant. So the number of significant standardized residuals in this case among the 20 most frequent response patterns is 0. Now, if you look at the bivariate proportions for the categorical variables, there's none that is significant. So here's a case then where the underlying normality holds quite well for these data, for these 16 variables. Now, how does that look when you use Bayes? Well, you have the same number of parameters, but you get a Bayesian posterior predictive checking result here using chi-square. And what you focus on is the posterior predicted p-value. Well, you typically also you really want these values to straddle 0, so minus and plus here. Posterior predicted p-value would be, for a perfectly fitting model, would be around 0.5. So the p-values operate on a little bit different scales, as we talk about in teachings on Bayes. So this will be a very well-fitting model. We certainly cannot reject it, which is expected since this PPP is chi-square based. Now, if you take a look at the most frequent patterns again, you see that the estimated values are a little bit different for Bayes, 97 instead of 98 for WSMV, and therefore the standardized residuals would be a little bit different. Some are worse and some are better for Bayes. But overall, none of them is statistically significant, and there's also 0 bivariate proportions that are significant. So once again, the model fits chi-squared naturally because it's an unrestricted model, but it also fits in terms of fitting the observed data in terms of the response patterns and the bivariate patterns. It also fits the univariate proportions, but I didn't list that here.